All right, factoring the difference of perfect squares and the sum or difference of cubes. Remember, difference just means a subtraction problem, and sum is addition, okay? So I always want you guys to look for a GCF anytime you are factoring. But because we're working with squares and cubes, it would probably be a good idea to go ahead and write out some perfect squares and perfect cubes. Okay, so what is a perfect square? Well, if you take a number and you multiply it by itself, the product would be a perfect square. So for example, 7 squared is just like saying 7 times 7, which gives us 49. 49 is a perfect square. What's a perfect cube? Well, let's take 7 to the third power. It's a perfect cube, or its product is 7 times 7 times 7 gives us 343. So 343 is a perfect cube. I would encourage you guys to memorize these values, or if you need to, especially right now if you're just starting out, go ahead and use a calculator and fill in these values, write these down on a sheet of scratch paper, whatever it is you need to do, but keep these handy because they will make your life easier if it's readily available, either if you've got them written down or you've got them memorized. That makes it even easier. All right. So let's look at some problems. Again, you always want to look for a GCF first. So our first example is 9p to the 7th minus 36p to the 5th power. Both of those terms are divisible by the number 9 and by the variable expression p to the 5th power. I can divide out 9p to the 5th from both of those, and we're left with p squared minus 4. So hopefully you recognize this is a difference and that p squared is a perfect square, but the number 4 is also a perfect square. So I know I have a special formula that I can use to factor this. And every single time, this is what I want you guys to do. Set up 2 sets of parentheses. We're going to have 2 binomials. What value times itself makes p squared? That's just p times p. So I have a p right here and a p right here. All right, what number times itself makes a 4? Well, that would just be 2 times 2. So in the back of our binomial, or of each of them, we'll have a 2 and a 2. Now, one of those values will be a plus and the other binomial will be a minus. And that's how you factor it every single time. But look, I forgot to bring over my GCF. Don't forget about your GCF. 9p to the 5th power, you're just going to bring down in every single step. And that is the factored form for example 1. All right, let's look at example 2. We have 81x to the 4th power minus 16. Hopefully you know that 81 is the same thing as saying 9 times 9. And x to the 4th power can be broken into x squared times x squared. So this entire first term is a perfect square. So is 16. 4 times 4 is 16. So we have the difference of 2 perfect squares. So let's go ahead and set up our binomial factors. One more time, what number or expression times itself makes 81x to the 4th power? That would be 9x squared and 9x squared. Okay, what number times itself makes 16? That would be 4 times 4. And every single time the pattern is plus and minus. And this only works for the difference of 2 perfect squares. It's never going to work for the sum. And if you don't believe me, you can go ahead and double distribute. Go ahead and double distribute, and when you multiply these out, you'll end up with 81x to the 4th power minus 16. Okay? So let's talk about factoring the sum or difference of perfect cubes. Look at this pattern right here. We have a to the 3rd power plus b to the 3rd power. Okay, both of those are perfect cubes. What is the pattern that we could break this into? Well, we have an a plus b. That's our binomial factor. And then we have a trinomial factor. It always starts with an a squared. It ends with a b squared. And then we multiply a times b for our middle term. Now, if this was a plus sign, we start with a plus sign. Then we do minus plus. Now, if I have a to the third power minus b to the third power, so this is the difference of two perfect cubes. Again, you start with an a and a b, but because this is a subtraction problem, you start with a minus b. And then our trinomial factor, we have our a squared to start, our b squared to end, and we multiply a times b in the middle. So you've got to remember your signs. Now, I know you're going to love this. I have a song, I have a jingle, goes to Jingle Bells to help you remember, okay? So let's look at, we'll look at the difference. The song is the same for both of them, okay? So if I have a cubed minus b cubed, it equals. I know that I'm going to go ahead and put down, I'll just pretend like I don't have this written, put my binomial and my trinomial parentheses down, okay? I know I have an a and a b, and then I'm going to start singing. So sorry. First times first is first. Last times last is last. First times last is in the middle. Isn't this a blast? The first sign's from the problem, which is a minus. The second is reversed, plus. The last is always positive, no matter what the first. Hey, jingle bells. Okay, so it's to the tune of Jingle Bells. But we could do it for a cubed plus b cubed also. Again, set up your binomial factor and your trinomial factor, okay? We start out with our a value and our b value, and then we start singing. First times first is first, so a times a is first, a squared. Last times last is last, b squared. First times last is in the middle, isn't this a blast? The first sign's from the problem, this is a plus. The second is reversed, so minus. The last is always positive, no matter what the first. Hey, jingle bells, jingle bells. Anyway, if you don't like singing, you don't like the sound of my voice, I'm sorry. I'm just trying to help you remember this, okay? So those are your formulas, or the pattern that you're going to use for the sum and difference of perfect cubes. So let's do some examples. We have 2x to the third power plus 54. So I look and I see both of those are divisible by 2. So when we factor out a 2, we're left with x to the third power plus 27. And this is where having your perfect cubes come in handy. X to the third power is definitely a perfect cube, that's obvious. But 27 is the same thing as 3 to the third power, or 3 cubed. So let's go ahead and break this down. We'll bring down our GCF of 2. Remember, we have a binomial and a trinomial factor. Okay, so x to the third power, that's an x. And then remember, 27 is the same thing as 3 to the third, so this is a 3. All right, here we go. First times first is first. Last times last is last. First times last is in the middle. X times 3, 3x. First times last is in the middle. Isn't this a blast? The first sign's from the problem. The second is reversed. The last is always positive, no matter what the first. And there you have it factored. Okay, let's try again. Example 4. We have 27x to the third power minus 1,000. Well, I look and I see this x to the third power helps me to clue in that it's probably the difference of perfect cubes. So is 27 a perfect cube? Yes, it's 3 to the third power. What about this 1,000? Is it a perfect cube? Yes, it's 10 to the third power. So let's break this down. We have a binomial factor and a trinomial factor. Okay, so what is the cube root of 27x cubed? That's just a 3x. What's the cube root of 1,000? What number times itself again makes 1,000? That's just a 10. So we've got that set up, and then we say, or sing, first times first is first, 9x squared. Last times last is last, 100. First times last is in the middle, 30x. Isn't this a blast? The first sign's from the problem, minus. The second is reversed, plus. The last is always positive, no matter what the first. All right, Let's do example 5. We have 24m to the third power minus 3. So I see that the m cubed here lets me know this is a cubic term, but look at 24 and 3. Those have a GCF. They have a greatest common factor of 3. So let's factor out the 3, and we're left with 8m cubed minus 1. And holy goodness, 8m cubed is a perfect cube, and so is the number 1. So here we go, 3. We have a binomial factor and a trinomial factor. So what number times itself again makes 8? That would be 2. And then m to the third power, that just makes m. What number times itself, what number times itself again makes 1? That, of course, is just the number 1. First times first is first, 4m squared. Last times last is last, 1. First times last is in the middle. 2m times 1 is 2m. Isn't this a blast? The first sign's from the problem, so minus. The second is reversed. The last is always positive, no matter what the first. All right, last example. We have 2d to the third power plus 128. So d cubed obviously is a perfect cube, but both of these values are even. So I can divide out or a GCF of 2. So we have d to the third power plus 64. Now 64 is a perfect square, but because d to the third power is a perfect cube, we're definitely going to use 64 as a cube instead of a square for this problem. Okay, so bring down the 2, set up your binomial and your trinomial factors. D to the third power, what does that break into? So this is a D, and what number times itself again makes 64, and that would just be a 4. We have that written down on the bottom of our paper, and now we can start singing or chanting, whatever. First times first is first. Last times last is last. First times last is in the middle. Isn't this a blast? The first sign's from the problem. The second is reversed. The last is always positive, no matter what the first. And there we go. So hopefully you have a better singing voice than me. Hopefully you don't wake up with nightmares tonight. Have fun factoring.